I think you all know me. It's a pleasure to be here. So, of course, I've been here since January. I joined as a collaborative biostatistician. I'm housed in the Department of Statistics in Blacksburg, in the College of Science. And I spent the spring building a Center for Biostatistics and Health Data Science, which I direct. And so today I'm going to take some time to discuss how researchers in health sciences can strengthen their research by incorporating careful analysis planning. And this is a version of a talk that I've been giving probably over the last 10 years through my work in the School of Medicine and School of Nursing at Penn as well, through their Office of Research. So the detailed learning objectives for the session, I think they're listed on the OCPD webpage. But basically, I want to talk about 4 best practices for planning quantitative research studies. 2 things to consider when sharing data, which I'm sure you've heard from Hart, and these are just things that we really try to hammer home pretty well as often as we can, and to really understand the importance of statistical planning. And it's such a key and important thing to do to make sure that you get your study right and don't encounter any last-minute crises. Talk about the components of a statistical analysis plan, ways to communicate data through tables and graphs and so on. I'll talk about variable types and then power and sample size as well. So to achieve those objectives, I'm going to walk through 4 ways to strengthen these studies, whether it involves the design of data collection, the prospective studies, or whether you're looking to analyze data that was collected retrospectively or you already have. These tips include seeking support from a collaborative statistician as early as possible in your research study, and like I said, include specifics about drafting this analysis plan, visualization, and sample size planning. And so incorporating these practices, it's an evidence-based model for increasing the likelihood of grant proposal success, and then as well as publication in peer-reviewed journals. So first best practice is to meet with your statistician as early as possible in your research process. I'm sorry, I am not telling you to move at all.
I've got you on collaborate with the statistician. Are you good?
Seek support early on.
Okay, there you go. Okay.
Yeah, there you go. So it's like I said, it's wise to seek support as early as possible. This is a well-known quote from famous statistician R.A. Fisher from 1938. To consult the statistician after an experiment is finished is often merely to ask him or her him or her to conduct a post-mortem examination. He or she can perhaps say what the experiment died of. And unfortunately, coming late is an uncommon scenario, but the bottom line is that we, including our group and Hart, will likely do what we can do because we know that busy clinicians really are up against hard deadlines pretty frequently. But what we don't want to see happen is that if you have a deadline for an abstract submission or a presentation or something like that, and then you come a week before and you realize that there's a fatal flaw in your data set, it doesn't have what you need, or it's collected incorrectly. So that's what we want to do, try to prevent that. Yeah.
It seems as if every time we have sessions on research, it seems as if people say, I try to contact a statistician, and we just struggle because there aren't enough statisticians here to put me in the queue, and by the time they really contact, they're able to have a meeting with them. Their study, maybe they're a fellow or something, and their study's too far along.
Yeah.
Are you all growing? Is that?
We're growing, and unfortunately, I've been doing this for 30 years, and it's really a common problem everywhere. But my goal is to make sure that folks get support. And so these practices that I'm talking about today are based upon, when I started my lab at Penn, it was sort of a culture shift to get people to think about things differently. Lots of times folks think that, well, they've had some baseline statistical training so they can do their analyses themselves. And then they go to find out that, you know, they're required to have a statistician on their study. And then when they start working with statisticians, you realize the important role that we all play together and how it does make such a difference. So I'm really trying to work at a culture shift here just for folks to understand the value of team science and the value of incorporating someone who really does this all the time on their team. But yes, that's why the early on push, so that we can certainly give the best services as possible, and folks are successful in their research endeavors. And the other thing is that, you know, if my collaborators are successful, then I am too, because my scholarship has nothing to do, I mean, it has something to do with me and who I am, but it really has to do with all of you, the people that I work with. And the reason I came to Roanoke is because of the level of scholars that are here at Carilion and at Virginia Tech, and I can just see that it was just ripe and fertile ground for the type of center that we're building and working with Hart as well, because it's just that the support and infrastructure had to be formalized, but the talent is here, it's been here, and it's going to grow with this campus that's growing. So yes, we're working on that. Was an awesome question.
And the way in which they contact you all to get this support, is it when you go through the IRB process and you say, yes, I would like statistical support, or what is the best way to contact you early on?
Okay, so I think that, I can't speak for Hart, but I think they might, that refers to their group. And for our group, we have a website, but we also have a link for requesting support, and it'll be at the end.
Great. Okay.
Also, you can certainly email me at any time.
Wonderful.
I can give you that information. So, move on. So this is resources in Roanoke, and I just said this. So fortunately, folks have two sources of statistics support here in Roanoke. It's our center and Hart, which we do provide very similar services. I understand now they're supporting grant proposal work, and they've been doing good research for a long time. Okay, so I'm at services. So I'm going to speak on behalf of our services, and like I said, I think that we're very similar. So we provide support for study planning, research activities, dissemination, and community building and education. So with regard to study planning, we collaborate with folks in study design, generating randomization schemes. We do a lot of power and sample size estimation. And in terms of research support, we do contribute to grant proposal writing. We serve as a data coordinating center. We perform data analyses, of course, including big data analyses and population health studies. We provide programming support in R, SAS, MATLAB, Stata, Python, and so on. And we love data visualization. I'm a nerd. I'm proud of it. And then regarding dissemination, we work with investigators to prepare abstracts, papers, posters, presentations. We work with you to generate your output, to help you understand it, to help you interpret it, and to present it. And then finally, with respect to education, we prepare and deliver guest lectures. We host educational workshops through our CTSA commitment, webinars. We sit on thesis and doctoral committees as well, and we advise capstones. So that's the education piece. And then for data sharing, I think that you all know this. Before sharing data, you're going to make sure that if it's necessary that we're added to your IRB, and please make sure that any data that is shared with us is free of any and all identifiers. And what we're asking folks to do, even though we do ask folks not to provide identifiers to us, oftentimes it still happens. And so we'll send the data back and delete everything, but it's still made it out there. So what we're asking folks to do now is to send us a data dictionary or crop contents, which is generated out of SAS, that gives all the variable names and types and things like that, so we can really look at it and make sure. But here on the next slide, we're providing actual list of PHI and then a link. And I know HART has this information on their site as well, and we do too. We have on our website, we have a bunch of frequently asked questions, and all this information is in there as well.
And so starting with the HART team, they can service the honest broker, is that true? Where they can de-identify?
I believe that is true. And yeah, and so they have services that we are not able to support. That includes, they have secure data storage, they do all the Trinetics work for study planning, they do a lot of the EPIC build, and I don't even know the language for it, but they do more of the EHR things, and certainly are experts in secure data storage.
Wonderful.
So when data comes to us, and I've really been living this way for a long time, so I'm really not, if I don't have to, I don't want to work with sensitive data. So then the next slide. So then the second best practice, again, is to work with your statistician to draft a statistical analysis plan. And the next slide is the statistical analysis plan, or the SAP, as it's called oftentimes in pharma. It is basically a document that in a very detailed way outlines your analysis plan for a quantitative research study. So putting this document together, it's an invaluable investment in time. It allows you, like I said, to very thoroughly and carefully evaluate what is the most appropriate methodology that you're going to use to analyze your data. And certainly careful data management and analysis planning will make sure that both your data collection methods and your database design will give you reproducible and reliable analytic results. Next slide. So what drives the analysis plan? This is a really important slide. You'll want to ask yourself several questions. You'll want to work with your statistician to work through these things. Oftentimes I sit with folks and actually help them hammer out their aims and hypotheses. You know, they have a great research idea, and then just talking about it with a statistician can help them really solidify it. So, you know, certainly you need to hammer out your aims, and then we talk about your study design. You know, does your study incorporate repeated measures over time? Is there clustering, like at the site level, at the PCP level, at the church level, at a classroom level, and so on, that needs to be taken into account as you perform your data analysis? And then we think about how your outcomes or your independent variables or your control variables are captured and measured. You know, are you using study instruments like the CESD for depression? And how are your scores computed? And then how are we going to analyze them? In other words, is it going to be on a continuum, a continuous measure of depression? Or are we going to dichotomize it and say depressed versus not depressed for each participant? So we really need to understand, once we say, how are we measuring outcomes or dependent variables? How are we measuring our predictor of interest or independent variables? What do we need to control for? What are the variable types? And then all the study design, then I go, okay, this is the way you need to do your data analysis. That's the most appropriate and sophisticated, but yet is publishable. Because oftentimes there's some pretty sophisticated analyses that are certainly appropriate. Oftentimes there are multiple appropriate analyses, but that might be not accepted or seen frequently in a certain area of study. So we kind of marry all those things, the appropriate methods with the field of study, and of course, you know, if someone is a frequentist versus a Bayesian, we take into account all these things. So answering all these questions, of course, we'll identify this appropriate methodology, and then once you have your appropriate method, then that tells you what is your method to use for sample size and power estimation. They're all linked together. It's a tightly woven story, and I do a lot of grant reviews for the NIH Corey, and this is the lens that I take as I review these grants. And the other stats. Yesterday, my panel had 4 statisticians on it, so it was really exciting conversation. But these are the things we look for. Make sure that power analysis is right in alignment with your statistical methodology, because oftentimes the power analysis drives. You're not going to. We'll talk about that later, right? So you need to know about variable types, right? So we have 2 broad categories. They are categorical and quantitative. This slide talks about categorical variables. So we will have nominal or ordinal variable types for the categorical. Nominal variables might be, eye color, ethnicity, Hispanic versus non-Hispanic, sex. It could be dichotomous with 2 levels, male versus female, or even other levels included. Smoking status, maybe with 3 levels, current, former, and never. Marital status, and so on. So those are categorical variables. And then we also oftentimes include ordinal variables. Likert type scales are a good example of ordinal variables, that like a 5-point Likert scale would range, say, from very dissatisfied to very satisfied, with neutral in the middle. Those are ordinal. Or say weight categories, ranging from underweight to morbidly obese. That's another ordinal variable. And then I mentioned dichotomous. The dichotomous variable is a subset of the nominal variable, just 2 levels. It's important to know that as a statistician, because oftentimes a very frequently used statistical analysis approach is logistic regression modeling, and that relies on a dichotomous outcome. In the next slide. And then we also have continuous variables and discrete variables. Those are our quantitative variables. Discrete variables are count variables, and oftentimes we'll use Poisson regression to model count variables, say number of hospitalizations in the last year, number of ED visits in the last year, number of falls, and so on, number of AEs. So that's a discrete variable. And then a continuous variable, of course, is one that's captured on a continuum. Like I said, CESD depression score, or say quality of life score that ranges from 0 to 100, weight, BMI, MMSE score, and so on. And again, knowing these variable types will lend, and knowing the aims, knowing the variable types will lend ourselves to choosing the appropriate statistical methodology. Okay? And this is an example table of a medical record, just as an example. So if this data set came to me, of course, we don't see any dates in here, names, and then these have been de-identified identification numbers. Then I would look at these and I would, find out, is this sex variable measured, which is 2 levels, then it would be dichotomous, age on a continuum, weight on a continuum, stage of disease is ordinal, smoking status here is no or yes, is dichotomous, race is categorical or nominal, and then number of meds, of course, is discrete. Quantitative variable. So that's an example. Next slide. And as I mentioned before, we can talk about statistical analysis planning from the perspective of primary data collection, which is prospective data collection, where you actually plan out your sample size and you go and you recruit people into your study. We design your database, collect the data, put it in there, extract it, and do your analysis, and so on. Or as I said before, using an existing observational data set, which is more of a retrospective approach. So primary data collection oftentimes is associated with randomized clinical trials. and specifically involve the study of interventions or drugs. And because of this, there's detailed guidance available out there about what should be included in a statistical analysis plan. So preparing this document is going to naturally lead to thoughtful consideration of the data that you're going to collect, as I mentioned before, what it's going to be used for, and how it's going to be analyzed. And it's also important for making sure that all of the necessary data is collected and that what you collect is going to be used. Okay, so next slide. So this is an example of a guideline document. It provides guidance on the content of a statistical analysis plan for clinical trials. So this appeared in JAMA of 2017, and I encourage you to take a look at it. Broadly, the SAP should include, your background and your objectives of your study, study design, randomization scheme, study aims, sample size, your framework that you're working within, any interim analyses that are planned, your timings of your assessments or data collection periods. You're going to specify your level of significance, multiplicity, and I'm going to talk more about what multiplicity is later in the talk. Your measures of effect that you're going to use, adherence and protocol deviations, as well as your analytic population. So you've got a target population and you've got an analytic population. You're going to talk about your trial population, your screening data, eligibility, recruitment, withdrawal and follow-up, and then you always want to have a baseline templates table. Having template tables is key as well. So you lay out empty tables on how you're going to analyze your data, and at the end of the day, how you're going to write your paper. So I tend to work closely with investigators to prepare papers, and when they come to me and say, hey, I really need to write a paper, I'll say, well, what's your objective and how are we going to tell this story? So we'll lay out the tables and the figures, and then we write around it. And so that way we know that it's a nice and cohesive story. And what we do is we write the statistical analysis plan. We write the statistics, the outcome section. We bullet point the results so that you guys can do your magic and make it appropriate for the journal and the readership that you're targeting. And then, of course, you really put your mark on it with the building up the introduction, and then the discussion is really puts it in within the context of the broader literature. Okay, so now the next, this is it. So what this is an example of a published statistical analysis plan from a clinical trial. So this was just published this year in April in Trials. So we don't typically see statistical analysis plans in the literature as of yet, but again, there's more attention to it these days. So I'm not going to spend much time on it, as I want to get to an example that I feel is more reflective of the type of work that goes on here, at least that I've been involved in the short period of time I've been here. But I encourage you also to look at this paper, and I've included the link here. Look at that. Next slide. Okay. So now we can switch gears. So we were talking about prospective studies. Now we can switch gears to the setting where a researcher seeks collaborative support after the data has been collected. So, this is an example of an interesting analysis that came to us a couple months ago. So the investigators basically are looking to quantify the impact of potassium on velocity outcomes, controlling for calcium and sodium. So velocity was measured both in two ways, longitudinally and transversely. The unit of measure was heart. So that was these measures were taken on 27 individual animal hearts. So you see, I'm going to ask about what type of variables these are. But so again, velocity is our dependent variable, two dependent variables. In this talk, I'm going to focus on one, just for simplicity. And it's a repeated measure design. So like I said, we have individual hearts, 27 of them, and each heart had measures of velocity taken in 2 directions for 4 different potassium concentrations, which were randomized to take into account the order effect, okay? Sodium and calcium, so there are 3 ions. There's potassium, again, we're interested in, that's our predictor of interest. And then 2 within the presence that we want to control for these other ion measurements, both at 2 levels. So this is the example we're going to work with. And then next slide. So, so this is asking the right questions. So once we've met with the team, then we ask some key questions so that we can put together our analysis plan, right? And so these questions, I say, okay, what is your primary research question? We talked about that. What's the relationship between potassium and velocity while we control for sodium and calcium? What is the dependent variable or outcome, whichever word you're more comfortable with, and what type of variable it is. So we're going to look at velocity, and it's measured on a continuum. Our independent variables, again, are potassium, sodium, and calcium, predictor of interest. Primary independent variable is potassium. The unit of measure is the heart. And the observations are not independent. And that's a key question that we ask because we need to take into account the correlation structure in our analysis. They're not independent because we have repeated measures on a heart. So one heart might respond differently than another, and we need to take into account that repeated measures on each unit. Okay, next slide. Okay. So, and I want you to take note of the plan that we came up with. So it includes our preliminary analyses, our data presentation, including our tables and visuals, as well as the analytic plan, okay? So we said we're going to do some descriptive statistics. We're going to present the variables that we have using mean, standard deviations, medians, interquartile ranges, and so on as appropriate. And we're going to visualize our data. I am a huge, huge fan of data visualization. It's very important to understand your data. Now, I want to step back a bit. This study is a data-driven study. It's an exploratory study within animal hearts that's used to generate hypotheses and support validation studies, either bigger studies in more animal hearts or move into humans. So a lot of data visualization goes there to understand relationships, understand what's going on, and to see if the hypotheses are being supported, or if there's anything else going on. The findings of this study, again, will be used to support power and sample size analyses and drive the primary hypotheses and questions for the next validation study. So we talk about our data visualization, and I'm going to show you examples of all of our graphs and figures. And then we used one-way ANOVAs at the very basic level, and then mixed effects modeling was our primary approach to take into account our correlation within repeated measures on a heart. Okay, so we used a stepwise approach given our small n, and we used the AIC criteria to choose the best model at the end of the day, where smaller values indicate a better fit. We also wanted to take into account the potential for nonlinearity, and you'll see how we did that as well. Next slide. Okay, so the third best practice of the day is effective data presentation. I want to make sure that I'm doing well with time. And please feel free to interrupt me as you have been. That's great. So to translate raw data into meaningful results, it must be processed, analyzed, and summarized, right? So, and most importantly, to translate our raw data into meaningful results, it means that this presentation has to be done effectively for our readership. So presenting your data can be a powerful communication tool, and it can present large amounts of complex information. So you want to be effective and creative with your presentation. So you can use text, tables, and graphs to present your data. Text is best for explaining findings, outlining trends, and providing contextual information. So graphs can effectively tell the story at a glance and can visually describe distributions, correlations, comparisons, and trends over time. Okay, so terminology. Okay, so the terminology univariate, bivariate, and multivariate sometimes differs by field. I tend to use the words univariable, bivariable, and multivariable because multivariate implies several outcomes to statisticians. So you'll see these multivariable and multivariate used interchangeably depending upon who you're talking to. So a univariate graph or a univariable graph might be a bar chart or a histogram, a single one, or a univariate analysis might be a one sample t-test. It's basically an analysis that involves one variable. A bivariate graph or analysis involves two variables, okay? So an example of a bivariate graph might be a scatter plot for two continuous measures, just looking at the dots and the relationship between those two continuous measures. Or you might look at side-by-side box plots for a nominal versus a categorical or a continuous variable. And those you'll see are my very favorite data visualizations because they show you so much information in a simple plot. And then finally, a multivariable figure or analysis incorporates more than two variables into it. And I'm going to show you examples of all that. So next slide. We talked about these basically. You can use tables for all types of variables, nominal, ordinal, discrete, and continuous. For bar charts, you're going to use those for nominal and ordinal variables. And then histograms for continuous variables. A bar chart and a histogram, they look very, very similar. There's just really subtle differences between them. But again, the bar chart is used for categoricals, histograms for continuous. Box plots are used for continuous variables, and I'm going to tell you why I love box plots in a minute. And of course, line graphs are usually bivariate, where your x variable is time and your y is some continuous outcome. It doesn't have to be. In our example, we're going to use potassium on the x, and then y would be velocity. And then scatter plots, of course, for two continuous variables is bivariate. Next slide. Okay. So table 1 is a very, very important table. That's the first table that you'll typically see in a manuscript that's published in a clinical journal. And it really describes the characteristics of the population that you wish to generalize to. So people can really get a good idea of what your population looks like. Typically it's socio-demographic and clinical variables that are included in it. Either overall and then stratified by your predictor of interest. And oftentimes, this is certainly not going to happen right off the bat, but what helps the investigators work with me and helps them understand their data better is if someone comes to me for support and collaboration, if I say, can you bring your table 1 filled out for me, then it really helps them clean up their data and really understand what their questions are as they ask how it should be formatted and so on. So it's a really useful tool. Next slide. Okay, so here's a table. This is our working example. And again, this shows basically our overall sample of 27 parts, and it provides, you can see here's our overall sample. And then within our 4 different combinations of sodium and calcium, these are our individual groups. So we have 5 parts with sodium and calcium levels is defined here, and so on and so forth, right? 5, 6, 8, and 8 parts within these different combinations. And within these combinations, you can see these are mean, this is transverse velocity levels. So you can see that they're significantly different across these groups, right? And then here's the p-value that comes from the one-way ANOVA. We have this for the various levels of potassium. So you can scan down the column to see if you have differences by potassium level. And if you look at these mean levels, you can see that you've got increasing velocity and then it decreases. So it looks like you've got a peak in velocity right here at this potassium level 6.4. Okay, so that's an example of a table. Now we have our figures, right? So let's see. These are examples of graphs that are commonly used in data analyses. So in the upper left, we have histograms depicting continuous outcome. So this is really a bivariate plot overall because it's showing you two different types of blood pressure and then systolic versus diastolic, and then the distribution of the blood pressure itself. The individual histograms, these are histograms, like I said, are univariate, right? But together, I'm calling that a bivariate plot. These are multivariable. This plot here is sort of complex. It's showing you suicide counts by age groups and male versus female. Okay, so you can see the distributions. This is skewed, as is this. You can see that among males, the counts are much higher. These scales are consistent here. And the peak for males is younger. And we have a bimodal peak for the females. These are the side-by-side box plots that I love. Why do I love them? Because, well, let me tell you what it is first. So this shows for a nominal variable that specifies the type of gene, an outcome. We're just calling this outcome value. This is just an example. It's continuous. But for each of these genes, you see the distribution of this outcome measure. And the distribution, it shows you, these boxes show you the first quartile of the distribution for the outcome, the median, which is the 50th percentile, the 75th percentile, and the minimum and the maximum, excluding any outliers. These two distributions in the middle demonstrate outliers. Well, how do you define outliers? Through these, you take the interquartile range, which is the difference between the 25th and the 75th quartile, and you take it and you multiply it by 1.5, add it to Q3, which is the 75th percentile, subtract it from Q1, and that's your limit for outliers. So these are min and max excluding outliers. So then you can see all these outliers. So you see these are skewed distributions. So what do they show you? The 5-number summary, minimum, Q1, Q2, Q3, maximum. They give you an interquartile range, and they tell you roughly if you have skew in your distribution. So we can compare these total distributions side by side for these genes visually, which is pretty nice. Okay, next slide. So in our example, so this is going back to our velocity and potassium example. So this is a multivariable display. It shows bivariate line plots for potassium and velocity within each of the 4 sodium-calcium groups, okay? So within each, these are bivariate individual panels, but as a sum, they're multivariable. So they're spaghetti plots, which are individual line plots or profiles for each heart. So these are individual hearts. You'll see 27 total lines showing the relationship. And you see this nonlinear relationship as we talked about before, right? So it's an inverted parabola. You can also see that if you compare these axes, as you're looking down, these are your sodium levels. The columns represent sodium. The rows represent calcium. And you can see as you increase the levels of each that the velocity is higher. Okay, so going over this way, increasing our sodium means increasing our velocity, and increasing our calcium, the same thing. And then you have a nonlinear relationship across potassium for all levels.
Alex, do you want to mention on that slide before that a lot of times gene data is transformed into log2 data?
Correct, yeah. So we use these visuals. First thing I do is I visualize my data, and if it looks like I have skew like this, you'll have to transform your data. And oftentimes a log transformation will normalize these distributions, and then of course normalizing your distributions allows you to use some more frequently used analysis approaches because they assume normality. Yeah. Okay, so now these are examples of graphs. So this is a multivariable figure, but it's an example of interaction plots, which are pretty cool. You don't see them in the literature often, but they're really showing a trivariate line plot of the relationship between sodium and velocity by calcium level. So basically it's meant to provide a visual of the interaction between sodium and calcium on velocity within each potassium level. So each point represents a mean velocity at the specific level. So each point is your velocity for the various potassium levels, calcium levels, and sodium levels. Okay, and so to determine whether or not, or to compare the effect of calcium versus sodium on velocity, you'll want to compare the slope of the line versus the distance between the points. So basically what we see here is that the difference between these points is less impactful than the slope of the points, or the change between sodium 145 and 155. So in looking at this, I see a nonlinear relationship, which we've seen over and over, between potassium and velocity. I see that calcium is less significant. Calcium is less significant than the sodium, and I also see the most important thing here is that these lines are roughly parallel, which tells me that there's no interaction between calcium and sodium. If they were crossing, then I would say there's an interactive effect, and I would have to include higher order interaction terms in my model. So that is extremely helpful for identifying interactions. Okay, so next slide. So these are final model results. This is a table. Now I would not use this table in a paper, of course, because it's just really too complicated. But what you do want to show in a paper, in a published paper, you want to show, of course, your effects. You typically don't include your intercept term, your level of your effects, your parameter estimate, your standard error, your statistic in your p-value, and your confidence interval. Okay, so you would want the readers to be able to really be able to interpret what's included in this table. But basically, as suggested by the interaction plots, the effect of calcium is quite small, not found to be statistically significant, and of course is not included in this final model based on the AIC criterion. When sodium is 145, the average velocity is significantly lower by about 3.4 units. And as compared to when sodium is 155. And the quadratic term is also highly statistically significant. So you can see that all these parameters that are left in the model are very significant in predicting velocity in this transverse direction. Okay, and then also I talked about the quadratic term. We saw that the maximums achieved at about 6.3 or 4. 6.3 for the actual modeling using the parameter estimates and computations that way. So next slide. So these are diagnostics. It's very important once you do your modeling. So you do your upfront visualization, then you do your data building, your analysis modeling, and then you have your diagnostics. So this top row shows model diagnostics for that final model. The upper left provides a scatter plot of the actual versus fitted dots. And you can see that the dots of the actually observed data hug this unity line quite well, which says it's a great model fit. We don't want them really to fall off the line at all. This is a plot of the residuals, a histogram. Of course, it's a univariate histogram. It demonstrates normality, which is exactly what we want. The colors indicate calcium versus sodium levels. And then finally, this is our fitted plot to the data from our mixed effects model, and it fits quite well the raw data. So this is bivariate as a whole, and trivariate as a whole, and bivariate individually. Bivariate showing potassium versus velocity. Again, these are scatter plots with superimposed predicted models. Next slide. So we talked about these interaction plots. The only thing I want to make sure that I touch on all the important things here. I've only added here the longitudinal plots because there was that second outcome, and you can see very clearly what's different about this one. Yes, exactly. So we have interaction here. So this final model was a beautiful model as well. I'm not going to go into it, but we incorporated interaction into it. Okay, so next slide. Okay, and finally, you always need to think about power and sample size, or at least discuss it with your statistician. As I said, when you're doing a prospective study, you really need to perform sample size calculations and power analyses. For retrospective studies, you want to consider it. You want to really have a good feel for what your power is given your sample size and your type of data that you've got. But as we saw before, your study design and your study aims, along with your variable types or your scale of measurement, for both your outcome and predictive interest, as well as your control variables, they dictate your analytic strategy, and your analytic strategy really directs you on what approach you're going to use for your sample size and power analysis. Okay? You're going to ask yourself, do I need to adjust for confounding? Does my data come from a cluster randomized trial? In other words, do I have independent observations, as I mentioned before? Are we going to do an intent to treat analysis? Do we have to specify in advance our multiple imputation or imputation approach? How do we assess our patterns of missingness? Because we know we're going to have it. Are there multiple comparisons that need to be considered, which is a very important consideration. Multiple comparisons come in various shapes and sizes. So next slide. So as you think about multiplicity, this might come with various endpoints or multiple comparisons or subgroup analyses. When I say multiple endpoints, you might be analyzing a data set or prospectively collecting data that includes outcomes of interest, hospitalizations, length of stay, physical and mental health from SF34, and quality of life outcomes. There you've got 5 outcomes. So if you've got 5 outcomes and you're going to generate 5 overall p-values for your predictor of interest on these outcomes, then your probability of making a type 1 error is 23%. It's almost 1 in 4, right? What does that mean? It means that you're going to say you have statistical significance when in fact it's just by chance alone. So you really need to pay very close attention to multiplicity when you're generating all these p-values and all these tables, and working with your statistician can really help you attend to that. So that was an example of having multiple endpoints, or you might have multiple comparisons. What if I have 4 treatment groups that I'm looking at, 3 dose levels and a placebo? And I want to compare 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, right? So if you have up to 10 p-values that you're generating, then your probability of a type 1 error is 40%. So you can see that it's like exponential growth of these errors. And they're very common when people do quantitative research. And then the last way you could see the need for adjusting for your p-values is in subgroup analyses, and we do those too, because you might do an overall analysis, but then within subgroups, maybe those at highest risk, or maybe by age groups, by ethnicity groups, race groups, and so on. You want to know measures of effect within those subpopulations. Then there you're also generating p-values on the same overall data set. So that is multiplicity. So next slide. So I also, this is really important to me personally. Sample size estimation is an ethical consideration. It's important to achieve this optimal balance. If your study is underpowered, in other words, you don't have a significant p-value, you might have a beautiful study that's generating great hypotheses, or that's really shown something that's clinically meaningful, and it ends up in a drawer because somebody didn't understand the power and sample size implications. So here they have something that's really meaningful, but they put it away. It was never followed up on, it wasn't published. That's an underpowered study. An overpowered study is one that includes too many subjects. Now that's an ethical dilemma as well, because you don't want to include people, enroll people in a study unnecessarily. You don't want to expose people to research if it's not necessary. So that's a very careful balance. You can also have overpowering when you're doing a big data analysis. You can find these clinically insignificant results that have a highly statistically significant p-value, right? So here's an next slide. Let's see. Actually, let me just tell you what the key components are to the sample size calculation. We'll go to the next slide there, sorry. So the key components that you're going to need to estimate your sample size are, of course, your null and alternative hypothesis. Are you going to do a one-tailed or a two-tailed test? What your significance level or type 1 error rate that you're willing to accept. Oftentimes that's taken to be 0.05. Your power, oftentimes that's taken to be 80%. In drug studies, you need 2 phase 3 studies powered at 90%. And then what's really, really important is knowing what's a clinically meaningful outcome. Oftentimes people don't know that. And what's been shown to be a clinically meaningful difference in outcomes is half of a standard deviation. So if folks don't really know what might be clinically meaningful, say an instrument hasn't been validated against functional things or what have you, we'll go with the half of a standard deviation. And you also have to know the driver, lots of times, of these sample size analyses is your variation. Statistics is all about variability. Okay, next slide. Okay, this is a table that I wanted to show you. So I work a lot with the UK Biobank and population studies, and this is a study that was, I think this one was just published actually in October maybe. So here we're looking at the interaction between, this is the study I was thinking of, sorry. I think this was published last year. But it again is using the UK Biobank. But what we have here is, let's look at this, because I know this study is totally overpowered. We've got, 416,000 observations in this data set, right? Here I'm comparing my incomplete versus complete data set because I want to get a feel for missing data patterns and if I have missing at random versus not at random. But the difference here in terms of age, again, because I've got such large sample sizes, I know I'm always going to have a p-value less than 0.001, highly significant. But does it mean anything? So I compute these Cohen's d effect sizes, and this is a very small effect size, so I say it's really insignificant. So this is a total example of having, observational data and overpowering. And then finally, I ran a power analysis for our working example with this investigator that we're working with here. And so this is based upon a mixed effects model because that was our primary analysis strategy. You want them to match. It was based upon 4 multiple measurements on hearts across 4 potassium levels. And then, of course, there's another grouping variable, and that was the 4 combinations of sodium and calcium. Okay, so what this shows is power for sample sizes of 5, 6, 8, and 20. Remember we had hearts in those various groups of 5, 6, 8? Well, it shows us, basically, that we do not have the power. We have 31% power to detect interaction effects. So if I were to put an interaction in that model that you saw, I wouldn't have any power to show statistically significant interaction effects. Well, if you remember, when we looked at the transverse direction, there really wasn't any indication of interaction too. So I wouldn't really want to include that. However, For the longitudinal analysis, there was evidence of interaction there, right? So I would want to be able to detect that significantly if I'm going to use this to design a larger study and really, move my research agenda forward. So what I would suggest to these folks is that they should study a total of 80 hearts in the next study, 20 per group if they want to replicate these findings and see if they're really real. And that gives us 93% power to detect a significant interaction effect. So interactions they require a larger sample size, of course. And this is all driven by variable types, number of predictors, number of repeated measures, and analytic strategy, right? This shows, so that's 20, right? 20 per group, but if you really want to get specific, which most people do because they're on a budget, you would say, well, I want 80% power. This is the interaction term, the power for it. So we want 80% power, right? So that looks like I need 60 some, right? 60 some. So maybe I'll need like 16 per group. I would refine this further. This is based on simulations and the mixed effects model.
So what did the investigator think of this?
He hasn't seen it yet.
Okay.
I just ran it for this talk, but we're in the middle of writing up his report for this. So I'm right in the middle of this analysis. Yeah. So this is actually for a TBMH student, I think. So this is how you can contact us. And we are thrilled to be here, honestly, and so excited. These projects are new and different to us because up in Pennsylvania we had different kinds of things that we're working on, and here I see more, working with these hearts and these ion levels, and I know it's going to be a different focus on things, more of the neuroscience things as well, working with stroke in children, and it's really exciting. The thing that I really love about my job is the exposure to all these different types of projects, and then of course the talent here and the ability to sort of create something in a support system so that folks can really move with their talent. So, do you have any questions?
So
Go ahead.
Alex, do you find that a lot of investigators really underpower their animal studies, and in some ways this is why stuff that works in animals generally doesn't work in humans?
Yeah, they do. And I understand it. I understand it's, a lot of these studies are expensive, but, I think simulation work could really contribute here. But yes, I do believe that there's a lot of underpowering, and I believe there's a lot of multiplicity problems, a lot of type 1 errors. So a lot of hypotheses that you see in discovery don't pan out, as they move forward into larger and further phase trials.
Yeah, that's always told people, like a phase 3 trial is actually very simple. It either works or doesn't work. It's usually based on one thing.
Yeah.
You said 90% power.
Yep.
And though you primarily work out of Virginia Tech, you're accessible to Carilion folks as well, is that true?
We are. We're typically the supporting the School of Medicine and FBRI, and then certainly any investigators. We're funded through the CTSA, and with the CTSA, we provide drop-in service. Not yet. Hart has drop-in service already, but once the new building opens and we have space there, we're going to have drop-in service like they do. But while we have time and while we're growing, we want to work with as many people as possible in kind, without asking for support. But the difference between Hart and us, I think, Francis, you can speak to this too, is we're going to, the way that our group is growing, we support a lot of funded research. So people write us into their grants. Right. That's how we're going to grow. So as we're at our capacity, we're going to be asking for funding. And if, for example, if groups, departments, or different groups are like, hey, we want to buy you out 20% of your time, we would love to reserve non-grant funds for people that just want their investigators to work with us. So we're open to all kinds of arrangements that way.
Okay, great.
I think that was it, what I was going to say there. Yeah. Okay.
Excellent.
Thank you.
Thank you so much. I mean, it's been, every time we ask research folks what they want to hear about when, people just starting out, they're, please give us some basics of stats, just to, whet our appetites, and then we can contact somebody personally to investigate further. So this has been wonderful. It's a great first step in getting people interested in knowing at least the terms to ask about. So some folks may not have even heard of multiplicity previous to now, and then they can use those terms when they're going to meet with a statistician to be informed in their conversation. So thank you, this has been very helpful.
Oh, you're welcome. It's my pleasure. And I know it wasn't about, basic tests like I looked at, previous work, but I thought, well, maybe just baby steps, introducing folks to us and then really trying to encourage folks to work with us to strengthen their science and how we think about things initially. So,
Yes, thank you so much.
you're welcome.